So let's take a moment and look at various definitions. Temperature. Well, that's simply a measure of the kinetic energy or the movement of molecules. That's at a very microscopic level, and it's true for both liquid, solid, or gas. The higher the temperature, the greater the molecular motion. Heat, which is energy, will move from a higher temperature to a lower temperature. And again, temperature is fairly intuitive. Dew point. Dew point is the temperature to which a gas must be cooled for that gas to become saturated. And by that, we mean that water condenses or dew forms, and that's why we call it dew point. It's the temperature at which dew first forms in a gas, the dew point. Unlike relative humidity, dew point is an absolute measurement, and we'll talk about that a little later. Dew point is independent of the temperature of a gas or of a room or a chamber. And the dew point is relatively constant within a chamber or a room. So that's why it can be a very good indication of how much water vapor is present in a space. Let's look at a real-world example of dew point. Here we have a dry environment. As one can see, the universal sign of a dry environment is the cactus shown in the window. If we were to take a beer glass out of a refrigerator, the temperature of that glass is above dew point, and the glass will remain dry. For example, if it was 25 degrees C and 20% relative humidity, the corresponding dew point would be about 0.5 degrees C. A fridge is typically about 5 degrees C, so that glass coming out of the fridge is warmer than the dew point. And as a result, no dew forms. The glass stays dry. However, if we had a condition where the humidity was much higher, and we took that same glass out of the fridge, we'd find that dew would likely form. In this case, at 25 degrees C and 50%, the dew point of the gas, or the air in the room, is about 14 degrees C. Again, the glass is about 5 C. It's cooler than the air. So dew forms because the temperature is below the dew point of the gas. Saturation. That's the maximum amount of water vapor that can be present in a gas, including air. Any more water vapor present, and it will simply come out in the form of dew, virtually raining out of the air. The definition of saturation is 100% relative humidity. In other words, the gas or air can hold no more water. It's at 100% humidity. This is a very temperature-dependent amount. The amount of water vapor that can be held is very dependent upon the temperature of the gas or air. Let's look at this graph. Here we're showing on the left absolute humidity. This is grams of water per liter of air. You can see it ranges from 0 up to about 0.6 grams per liter. And along the bottom we have the temperature of the gas or air. At 0 degrees C, we can see that the air is not capable of holding much water vapor. And as we move up to 100 degrees C, we can see that the amount of water vapor that the air can hold is much greater. At about 20 degrees C, or room temperature, we see that the air can hold about 0.02 grams of water vapor per liter of air. So relative humidity is the amount of water vapor present in the gas or air as compared to the maximum possible. It's very temperature dependent. Let's look at that previous graph, but we've zoomed in a bit here, sort of around room temperature. If we were to take 22 degrees C, or 72 F, we would see that the maximum amount of water vapor that can be held in that air is 0.019 grams of water per every liter of air. So that's 100% relative humidity. Now, if we took half of that amount, 0.0097 grams of water vapor per liter of air, that would be 50% of that maximum amount. And that's our definition of relative humidity. 50% of the saturation is 50% of the relative humidity. If we had a quarter of that amount of 0.019, in other words, 0.0048 grams of water per liter of air, that would yield 25% relative humidity. So relative humidity is the percentage of water vapor that's present as compared to the maximum amount possible, or saturation. Now, if we were to keep the amount of water constant in a room or a chamber and simply change the temperature, what would happen? Well, here I'm showing something called mixing ratio. It's also an absolute measurement, and it's shown in grams of water per kilogram of air. So in this example, we have 9.88 grams of water for every kilogram of air. And if the temperature is 25 C, we would have 50% relative humidity. Now, if we kept that same amount of water, in other words, 9.88 grams of water per kilogram of air, and simply changed the temperature, in this case to 15 degrees C, we'd see that the relative humidity would go up substantially. Now, if we were to take that same amount of water in the air, keep it constant, and increase the temperature, we would see that the humidity drops considerably. Now, in all of these cases, we can note that the dew point stays constant. That's because dew point represents the absolute amount of water vapor that is present. So although relative humidity may change and is very temperature dependent, the dew point stays the same. Now, if we were to keep the humidity constant in a room, this table shows us how much we would have to change the water vapor content in that room. So if we wanted to maintain 50% RH, here starting at 25 C, as we saw before, 9.88 grams of water per kilogram of air would maintain the 50% value. If we change the temperature to 15 C, we would have to decrease the amount of water, in this case to 5.28 grams of water per kilogram of air. And if we were to increase the temperature, yet we wanted to maintain 50% RH, we'd have to increase the water present by a substantial amount, up to 23.5 grams of water vapor for every kilogram of air. So we can see if we want to control humidity and keep it constant, we really need to change the amount of water vapor present as the temperature changes. So we can see RH is very temperature sensitive. A small temperature gradient can introduce quite a large change in relative humidity. For example, at 25 C and 50% RH, just a 1 degree C temperature change can cause a 3% change in relative humidity. And at 40 degrees C and 75%, a 1 degree C temperature change will cause a humidity change of 4% RH. It's very temperature dependent.